Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Each week for the next several weeks, I will be releasing sample questions for each of the 4 AP Physics exams to demonstrate to students what typical free response questions are like and how they can expect the exam to ask them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not all students have the opportunity to work with released exam materials prior to exam day, and this video series is primarily intended to help those students. AP Central lists the following types and number of free response questions students can expect to see on the AP Physics C Mechanics exam, including experimental design and a lab-based component. And then on the whole, the questions will assess all 7 of the science practices listed here. Today we're looking at the C Mechanics exam question number 2 from 2016, which covered conservation of momentum and energy, Newton's laws, and simple harmonic motion. A block of mass 2m rests on a horizontal frictionless table and is attached to a relaxed spring as shown in the figure below. The spring is nonlinear and exerts a force f of x equals negative b times x cubed, where b is a positive constant and x is the displacement from equilibrium for the spring. A block of mass 3m and initial speed v0 is moving to the left as shown. Part A, on the dot below, which represents the blocks of mass 2m and 3m, draw and label the forces, not components, that act on each block before they collide. Each force must be represented by a distinct arrow starting on and pointing away from the appropriate dot. So on the block of mass 2m, we are going to have its gravitational force. I'm going to call it gravitational force 2 because it's the 2m block. And then we are also going to have an equally sized normal force that I'm just going to call normal force 2 because, again, it's on the 2m block. And then over here on the block of mass 3m, we're going to have a gravitational force. I'm going to call it Fg3 because, again, it's on the block of mass 3m. And I'm going to call it normal force 3 just because, again, it's on that block of mass 3m. So here's our scoring. Pretty short and sweet for this one. So we have 1 point for drawing and labeling the forces on the correctly drawing and labeling the vectors on the block of mass 2m. And then likewise, we're going to have another point for drawing and labeling vectors on the block of mass 3m. And then an important note is that there is a maximum of 1 point that can be earned if there are any extraneous vectors. Now the 2 blocks collide and stick to each other. The 2-block system then compresses the spring a maximum distance d as shown below. Express your answers to parts B, C, and D in terms of capital M, B, V0, and physical constants as appropriate. So for part B, determine an expression for the speed of the blocks immediately after the collision. Well, that's going to be pretty straightforward. That's just going to be a conservation of momentum type of question. So P initial equals P final. And so all of our initial momentum exists in the block of mass 3m moving with speed v naught. And then after the collision, the two move together. So 3m plus 2m with the same final velocity. And so we're going to get an expression for that final velocity after the collision of 3/5 v naught. And our scoring here, 1 point for correctly substituting into a proper expression for conservation of momentum. I'm just going to write that as cons of MOM, abbreviate just to save a little time, conservation of momentum, and then 1 point for a correct answer. And part C, determine an expression for the kinetic energy of the two-block system immediately after the collision. That one likely is not so bad, so we're going to remember kinetic energy is equal to 1/2 mv squared. So we simply need to substitute. We have a total mass of 5m moving together after the collision and moving at a speed 5 v naught, the whole quantity squared there. So let's expand everything. That's a 5m. And then here we have times 9/25 v naught squared. And that's going to give us 9/10 m v naught squared. And our scoring here is 1 point for an answer consistent with part B. So notice that you don't have to have gotten the correct answer here. And this is something that is common across all 4 AP Physics exams. If you mess up getting an answer on an earlier part of the question, but then you use it correctly in subsequent parts, you can still get full credit on those subsequent parts, even if you made a mistake the first time you answered the question. Oh no! Part D, derive an expression for the maximum distance d that the spring is compressed. Well, this is a conservation of energy kind of question, right? Because we're going to have the kinetic energy just after the collision is going to be equal to the elastic potential energy upon compression. And we are going to need to remember that, we're not going to be able to do a simple 1/2 kx squared here because it's a nonlinear spring. So our elastic potential energy for this nonlinear spring is going to be equal to the negative of the integral of f of x dx. So we can take that kinetic energy from just after the collision, 9/10 mv naught squared, and we're going to set that equal to the opposite of the integral from x1 to x2 of negative bx cubed dx, which will pull the negative from inside the integral outside. Negative of a negative is a positive. So we'll integrate from the first position to the second position of b times x cubed dx. And now, in the next step, we'll go ahead and talk about the proper limits of integration. So our problem situation showed that we're going to integrate from a position of 0 to that maximum compression of d, that is a capital D, of bx cubed dx. And when we then evaluate that integral, we're going to get b times x to the fourth over 4, which we will evaluate from 0 to d, and that gives us b times d to the fourth divided by 4. That is now equal to our 9/10 m v naught squared. And I won't show you all of the algebraic steps here, but you're going to end up with the fourth root of 18m v naught squared divided by 5 times that constant b. Let me clean up a couple of those things, make it a little bit clearer. Alrighty. So scoring, we're going to need 1 point for a correct expression of conservation of energy. We are going to need, or we're going to get a point for attempting to integrate the spring force equation. We are going to get a point down here for our correct limits of integration. Or an appropriate constant of integration. And then our final point is going to be for an answer consistent with the speed from part B or the kinetic energy from part C. So that shows up again where if you made a mistake earlier on, but you've used your expression correctly here, you can still get full credit here. Part E, 1. In which direction is the net force, if any, on the block of mass 2m when the spring is at maximum compression? Left, right, or the net force on the block of mass 2m is 0? Justify your answer. My pro tip here is when you are asked to make a selection and then justify your answer first and then come back to make the selection. Because you can't make an accurate selection until you've thought everything through, and justify your answer is the place for you to do that thinking and record your thought process. So for this question, at maximum compression, the two-block system is instantaneously at rest. The only horizontal external force acting on the system is due to the spring. This force is directed to the right. The system, including the block of mass 2m, is accelerated to the right. This is both as the blocks are moving the spring and compressing it, the spring's pushing back to the right, and then at that moment of rest, we're still being accelerated to the right. We still have a rate of change of velocity. And so with the system being accelerated to the right, that implies the net force acting on the block of mass 2m is also to the right. So we will check that. And our scoring here. Oh, I did it again. There we go. I lost my stylus. It happens at least once every video, sometimes more than once. So we're going to get a point for selecting the correct answer of right. With a reasonable attempt at a justification. And then our second point, and this is a lot to write, so I'm actually not going to write all of this. We're going to get a second point for indicating that at maximum compression, so I am going to kind of highlight this though, just to make it a little bit easy. Actually, we'll write 1 point for the following things that I'm going to highlight for at maximum compression. The block of mass 2m is accelerated to the right due to forces acting on the block of mass 2m. And then there's some extra explanation here. Or you could talk about an acceleration to the right due to the external spring force acting on the system of blocks. So let me change my highlighter color here. So if you talked about this bit that I'm highlighting in orange, this would be also something you could talk about that would earn you this second point. E part 2, which of the following correctly describes the magnitude of the net force on each of the two blocks when the spring is at maximum compression? Our choices are: the magnitude of the net force is greater on the block of mass 2m. The magnitude of the net force is greater on the block of mass 3m. The magnitude of the net force on each block has the same non-zero value. The magnitude of the net force on each block is 0. Justify your answer. So let's start with that. Because the blocks stick together, both blocks must have the same acceleration. Because the block of mass 3m has more mass, the net force on it must be greater than the net force on the block of mass 2m. And our points are going to be coming from the indication that the blocks must have the same acceleration. I'm just going to highlight that just to make that a little bit easier. So your first point indicating that the blocks have the same acceleration. And then your second point is going to come from the correct justification for why the net force is greater on the block of mass 3m. And then there's also a note in the scoring guidelines that if an incorrect selection is made, No points are earned for the justification. In part F, do the two blocks, which remain stuck together and attached to the spring, exhibit simple harmonic motion after the collision, yes or no? Justify your answer. Because the blocks are sticking together and are attached to the spring will apply a restoring force to the blocks. However, because the restoring force exerted by a nonlinear spring is not proportional to the block's displacement from equilibrium, the blocks do not exhibit simple harmonic motion. So we'll select no, right? Remember that we are talking about the fact that that is the hallmark of simple harmonic motion, is that the force is proportional. It's a restoring force that has to be proportional to the displacement. Like, that's what this means. That's not going to happen with a nonlinear spring. So let's talk scoring. We're going to get a point for selecting no. With a reasonable attempt at justification. And then our second point is, again, I'm just going to highlight. It's really sort of like starting here and everything that comes after. Let me grab the highlighter. The fact that the restoring force exerted by nonlinear spring is not proportional to the block's displacement from equilibrium. The blocks do not exhibit simple harmonic motion. So your second point is going to come from all of this. And then we have again that note. Give me just a moment. We have again the same note. Oops. Hang on. I thought I grabbed red for this. Red. There we go. Same note that if you've selected, actually the note here is that if the correct answer is selected without justification, hang on, let me just clean up my handwriting just a little bit. It's funny because my cursive is so much prettier and easier to read than my print, but it's harder in a video for people to read cursive. Without justification, the point is not earned. We had another note that similar to that last section, like if an incorrect selection is made, no points are earned for the justification. So I hope you have found this video on an APC mechanics question for a nonlinear spring to be helpful. And this is another one that shows how the AP C Mechanics exam can weave together multiple topics in the same question. If you have a video solution request for YouTube that you would like me to post, you can send it to physicsproblemrequests@gmail.com, but I won't be doing any of them until my AP series is over. If you would like some email assistance, you can send your question and the work you've done on it to freephysicshelpline@gmail.com with a limit of 10 questions per academic year. If you'd like to know more about my online physics tutoring services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics C Mechanics exam, and those materials include the release free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these released exams live, and to see what the scores for that year were looking for and how they decided to award points. If you have any questions, you can reach me at brandyheflinphysics@gmail.com. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.